Good morning. Welcome back to our plenaries. Hope you saw some good papers this morning. There are several very good ones, actually, early on. This is the 5th plenary. It's a special, as you know, this year. We're doing a number of plenaries because we need to catch up with our 50th anniversary. We have seen already keynotes from Qualcomm, from DARPA, from NXP, from IBM, and today we'll be hearing 2 more from EPFL as well as Volkswagen. We have 1 more plenary in the afternoon. We also saw visionary talks from Synopsys, from PDF Solutions, Mentor Graphics, Mubadala, and we will see the one from Teradyne today at this session, and the one from Advantest later on this afternoon. Before doing so, in the first plenary, I mentioned that we have the Doctoral Best Thesis Awards to be given. That competition was yesterday. As you know, this is a competition that carries the name of late Professor McCluskey. This is the best PhD thesis in the domain of test. We do the semifinals in several test conferences at VTS, ETS, ATS, and LATW, and the semifinalists do compete here at ITC. And that session took place, and the juries, and we do have an academic jury and an industrial jury. They look at the technical value and the applicability. And therefore, we have the results with us, and I'm happy to announce the winner of the Best Paper Award this year, and that will be Tao Chen from Iowa State University. Tao, are you here with us? Okay, so Tao receives this award for his work on built-in self-test, self-calibration for analog and mixed signal circuits. He presented this at the competition, the local competition at VTS, and he will be receiving the certificate from us, and he'll be the best doctoral thesis winner of this year. Of course, there are several things that correspond to that as well. Another award that we typically mention it at this session is the joint award of JETA and TTTC. JETA and TTC together have an award that we do for the best papers of the previous year. That is for the entire year of 2018. The papers published in JETA. We have a dedicated selection committee that does that. The winner this year is a team with a paper called Address Ramping Techniques for Enhancing Fabrication Yield of Embedded Memories. Masaki Hashizume, Haowei Lin, Xiu-Kui Lu, and Hao Cheng Feng. If we are here, please, if you're in the room, please come by to receive your awards. Winning team, missing team. I guess we'll see them later. I have your certificates here, and I'll be more than happy to present it to you. Okay, moving on. Nani, you have 1 more minute then, since they were not here. Our next speaker is Giovanni de Micheli, even though it says Giovanni, but he is Nani. Nani is a very old friend, an excellent speaker, a very prominent person in our domain. He is currently the director of the Department of Electrical and Electronic Engineering. It's a center at EPFL. EPFL is the École Polytechnique Fédérale de Lausanne. It's in Lausanne. He used to be at Stanford previously. Professor de Micheli, he is in Lausanne in Switzerland for some time now. He is a fellow of IEEE, fellow of ACM, as well as a member of Academia Europa, and an international honorary member of the American Academy of Arts and Sciences. His research interests are in design technologies, integrated circuits and systems, and particularly synthesis of emerging technologies, network on chips, and 3D integration. He has many, many awards, a few of which we can mention. 2016, he received the IEEE Computer Society Harry Good Award for seminal contribution to design and design tools of network on chips. In 2016 also, he received the EDAA Lifetime Achievement Award. A little bit before that, in 2012, he received the IEEE CAS Mac van Valkenburg Award. And he has many other awards as well, but we're excited to hear his speech. Nani will be covering with us this topic. All yours.
Thank you so much, Yervan, for inviting me here and for the kind introduction. I set up a title which I think goes very well with the mood in Washington this day, but my talk is going to be on technology. I will actually spend a little part about talking about devices and upcoming devices, then talking about the majority paradigm in logic synthesis, and conclude. So one key aspect in circuit is related to decision making. Now, we are in the CMOS age. We had CMOS circuits for many years, and we probably will. But CMOS has one particular way of thinking. If you think CMOS circuits are designed based on NANDs and NORs, these are the primitives, and there a decision can be taken just by one controlling variable. So for example, a single 0 can force a NAND to be true, and conversely for a NOR gate. In the different settings, we can see that some new technologies exploit the majority function. The majority out of 3 function, for example, is such that if 2 inputs are true, at least 2 inputs are true, then the output is true. They do the majority on the inputs. And majority is defined, of course, over any number odd of inputs. Similarly, we see a lot of interest in neural networks application to AI, and they are often based on threshold functions. And threshold functions can be seen as weighted majority gates. So there is a strong link between threshold and majority logic. Now, the principles of majority, of thresholds, have been known for at least 50 years. They were studied heavily in the 60s. And then not used much because actually CMOS has a different structure. But still, tools, design methods, design flows for majority have not been exploited yet, or at least on a large scale. So let's just make one step back and look at technology. Where is technology leading us? We know all the problem of variability, scaling down transistors. There is a renewed interest on Schottky-based design. And here I show you a design in silicon where you use still an old material silicon but with a new geometry, where you can control the transistor to behave as P or N using a field that is called electrostatic doping. So you avoid to dope the transistor, you can make it small, and you don't have the variability there. What's also interesting in this type of gate is that the fundamental switch is not just a switch, but it's a comparator induced switch. And this helps to build effective XOR gates, which is absolutely important in many circuits. That's an implementation. Thanks to Photoshop, you can see the silicon in green, and you can see the gates in purple and in violet. Now, coming to a different material, but with the same principle. Much has been said about graphene. Graphene is not much used today in circuits because it lacks a band gap. But other materials that are 2D materials have been used, including, for example, MOS2, molybdenum disulfide, and wolframium diselenide. This picture here shows an experimental transistor that can behave again as a P or as an N transistor, according to the polarization. And this picture shows a XOR gate realized with this material. Interesting enough, with this material, as in the case of the Schottky-based silicon devices, you can build cells, NANDs, NORs, XORs, that have the same size, just with a different topology. Now, let me come to something that's more exotic. The AQFP, that's a technology that's been developed in Japan mainly. It's for superconductor circuits where we actually store information in loops, in current loops. In fact, we take a logic view of these gates actually are implemented by buffers that once connected together implement directly the majority function, and where inversion can be applied at the input of the gate in a very simple and straightforward way. Again, this is an implementation of superconducting technology done in Japan. There's a similar one done in the US, which is based on the work of Likarev. Now, the point is that if you look at various nanotechnologies, like, for example, superconducting, like ReRAMs that are used as in-memory computing, like optical-based technologies, there are many physical effects that actually can map directly to an abstraction as majority function. As a result, I'd like to stress two key points. Some of the emerging technologies that we have implement multi-gate transistors where you have a device-level programmability, and they realize quite nicely comparators, that is XORs as well as majority. And then you can also use this opportunity to start digital design based on different primitives. Instead of thinking of NAND, NORs, and inverters, or basically our cell libraries that we use every day based on A or I, we could actually design circuits based on XORs and on majority gate. Now, interesting enough, this is also applicable to CMOS. It's an opportunity that's been overlooked for many years. So the rest of my talk, actually, which deals with the majority paradigm in logic synthesis, is applicable to both the emerging technologies and to CMOS as we have it today. So why majority? Well, because majority has sound mathematical properties better than the properties of the circuit model that we use today. So it's an opportunity to design better and faster design. The majority applies well to emerging technologies as well as to CMOS. It can be used to build threshold function, which is also very important. And I like to actually stress a statement that appears in the volume 4A by Dola Knuth, I think one of the greatest scientists that we have still alive with us, that say that majority of the inputs is probably the most important ternary operation in the entire universe, because there are properties that are continuously discovered and rediscovered. Actually, volume 4A came out just a few years ago. Research on majority had been going already for years, but it was really refreshing to find out that a person like Knuth, who starts from theory to justify circuits, finds this importance in this primitive. Now, why is that from a practical reason? Well, because if you build a gate that could be, for example, a part on FPGA with majority, you can make it easily into an AND or an OR gate by sticking an input at 0 or at 1. And this actually opens up opportunities in optimization that were not seen before. For example, here you see a AND-OR decomposition, which is optimal with respect to the properties for implementing a function. And here you would see one that you obtain with a majority tree gate, which is smaller. Of course, you would object if you use 3 input gates, you get something that is smaller. And so let's go through the exercise of mapping this to a library. So we take a simple library that everybody knows, genlib. And here we have the 2 starting parts. We just map them to gates. And you would see that the area is smaller in the majority-based starting point for doing technology mapping. But then we can say, well, genlib doesn't have per se majority gate, so let's add a minority gate, which is actually a majority complementer that works well in CMOS. And it's a gate that is quite used by people who do adders and multipliers. And if you do that, then you will see that area and delay both go down. Of course, this is one example. We have to make this more general in order to be credible. So how to exploit majority logic? We want to have good, scalable models to manipulate majority. And today, most of the advanced logic synthesis tools manipulate graphs that have AND, OR, and XORs, and we want to replace this by MIGs. For us, MIGs are not Russian fighters, are basically majority inverter gates, that majority inverter graphs, that are graphs that use nodes that represent the majority function and bubbles that represent inversion. So this is a simple MIG for 3 inputs. Everything is generalizable to 5, 7, and more inputs. What I'm presenting to you is with 3 inputs because it's simpler to understand, but the properties are the same. So how do you manipulate logic? You can define on this data structure some very simple axioms on which to define the algebra. First property is commutativity. That basically means no matter when you vote, your vote counts the same. The second one is majority, that says that if you are 3 and if you agree, if 2 of you agree, you win. If you disagree, it's the third person who decides. There are associativity and distributive property that allow you to rewrite expressions so that inputs come in with a different level of stages towards creating the final result. And there's a final property which is interesting, which is self-duality or inverter propagation, that says that the complement of the function is equal to the function of the complement. So graphically, if you go back to the graph, you can have the bubbles that represent the inverters flow through the graphs up and down to create for you the implementation that is most useful. What's interesting is that if you set up an algebra like this, starting from these postulates, instead of starting from the typical axioms of Boolean algebra, you obtain, of course, a Boolean algebra based on operators majority and complementation. This algebra has, though, some nice property, because this algebra has the property of being sound and complete, that basically says that if a formula is derivable from the axiom, a graph is derivable from them, then it's valid, and vice versa. And this has a very important consequence, that the state graph is reachable. That is, suppose you have a configuration of your circuit, that it's here, that's what you know. You have another configuration of the circuit, that it's there, that's the best one, the one that you want to reach, and you don't know how that is. Then there is a path that goes from here to there based on the transformations or a composition of the transformations that I've shown you before. Of course, this path can be long, it can be hard to find, but is there. Without a representation of logic, this path may not exist, and so you may be prevented from finding a best solution or the solution that you look for the given clock rate that you want to achieve, even with infinite computing power. So how do we optimize then these graphs? Very simply, we can do it by stepwise transformations. And what we care about, we basically care about reducing the area that relates to the size of the graph, the delay that relates to the critical path, and the power, which relates to the switching activity that is inside the model. Few examples on how to do this. So if you want to reduce the big size, you can use some properties. So if you can apply majority, then you would reduce by 1 node. If you can apply a distributivity from right to left, you'd also reduce 1 node. As you can see, these are very simple transformations. You have to apply many of them as well as combination of them in order to get result. What about if you want to make the circuit faster? Again, you can use majority because it will reduce 1 level of delay, but also you can use other properties that allow to swap variables, that is, they allow you to bring in variables related to late incoming signals closer to the output. So this transformation can be seen as algebraic rewriting transformations that give you a circuit with better properties. Now, let's try to apply this to others. This is the description of others in terms of simple gates. This is the mapping in terms of MIGs. And these are the result of applying the techniques of rewriting the others to search for the fastest adder, starting from a slower adder. So interesting enough, for many examples, a tool can find out a structure which has the same level of delay as a carry-looker-head adder, starting from a regular adder. So this is extremely important because finding out automatically a fast carry structure has always been a hard problem. But being that still a heuristic, it's not guaranteed to work on all the types of adders that are there. And actually, this is just an example. This technique is not meant to do adders. We want just to show that on a specific type of block, where we know what the best design is, we can get, most of the time, close to the best design. So we have developed tools, because all this is good if you can try out on many types of circuits. And the tool is called MIGHTY, starting from MIG. And we try to compare with existing tools first, based on the notion of area, size, and switching of the related graph model. So here we are comparing to BDS, the tool based on BDD, University of Amherst in Massachusetts. That's the gold one. The blue one is Berkeley, the work on AIGs of Mishenko and Brayton. The red, kind of Stanford and EPFL, is the work of MIG. So the result is that the techniques are comparable in general, except for speed, where MIG actually can do better by 20% as compared to AIGs, and so it's interesting. So you could say, well, up to now you have been manipulating graphs. This is not real design. In real designs, there are many other things. So what we did experiments on CMOS. We took an advanced 22 nanometer set of designs, and then we did the following experiment. We took the design, the benchmarks. We passed them through our tools, MIGHTY, and then we passed them through a commercial logic synthesis and physical design tool. Then we did the same thing without using the manipulation based on majority. So doing that on benchmark, we obtain a 15% average improvement in speed, with still an improvement of 5% in area and power. And all these designs were, of course, verified formally to make sure that we were getting something correct. This was done using a script for speed, so the major advantage was its speed as compared to area and power. But we could, of course, do it in a different way. Then we tried to say what happens if we take an IP block that is known. And so we took an example of a divisor, 32-bit divisor as an IP block. This was a 90 nanometer, because that was the example that we had available. We got the original one, we got the MIG optimized part, and the results were that the area and delay went down in both cases by about 15%. The the gate count, GC, also went down. Again, in this case, we did verification. So the idea is that we started from a design technology, a method based on majority, which is motivated by emerging technologies, and we applied it to CMOS, and we showed that on CMOS it can do better than existing strategies. Of course, on CMOS you can make experiments because you have many benchmarks and you know what the results are. If you go to emerging technologies, then you are in a very unknown territory. We tried on speed wave devices where we don't have the realization, but we have the design of many circuits. Here there's a table. It's complicated. You can actually look at only the last row. But it showed that the delay that was simulated from a structured design with MIGs was better by about, again, 10 to 15% as compared to one that was designed using more traditional technique like AIGs and the tool ABC from Berkeley. We also tried on a double-gate silicon nanowire FET model, as you've seen in the beginning of this talk, on a 22 nano. Again, this has been model simulated, not realized physically because these are experimental design techniques. You can make devices, you can make transistor cells, but it's hard to make big components. And these are the results that we obtained by doing comparison. We were able still to reduce the delay by about 15%. In this case, we got an area increase and also a gate count increase for this design. So not everything is under control, but for most of us, speed up the circuit is the most important thing. Some key points. This majority inverter graph with the Boolean algebra basically push further the capabilities of modern logic synthesis. We know that with logic synthesis, we don't get to the best design. It's too hard. But the important thing is to not to outrun the bear, but to outrun your competitor. We get significant improvements for general benchmarks and also for highly optimized blocks. And of course, we have a set of tools that can support emerging technologies. And for example, at present, I'm very much interested in seeing what happens with superconducting technologies, because you can achieve computation at very, very low power and very, very fast. Let me try to draw some conclusion. First, let me just pull one moment back from technology and let's look at the big picture. We have in front of us many complex embedded systems. Take, for example, the self-driving car. You have a lot of sensors, you have a lot of input data. It's very important to average the data and have a result in aggregate, many times. That's important in order to have a safer operation. A few things may go wrong, but you want to be able to filter out this wrong decision if you have many data acquisition points. That's why majority is important. We also talk a lot about a green world, green electronics. It's very important to reduce as much as possible energy consumption for given performance constraints. So if we set them, tools that actually use majority logic in design can lead us to achieve circuits that consume less power as compared to those that don't use it. So that helps us also to have a greener world, greener industrial world. And finally, the emerging technologies will benefit directly from majority logic synthesis because majority is the native abstraction. So in conclusion, I would like to say that, our work as scientists, as engineers is never finished. We have new design, new synthesis, new verification methods that can come out from new abstractions that we have of the physical reality, of the reality of the CMOS that we push to the very end, as well as the new emerging technologies in silicon, in CNTs, in 2D technologies, and so on. As far as logic design is concerned, logic synthesis is based on heuristics. Having new models, we can push further the limit of logic synthesis in order to get better results for both CMOS and emerging devices. And finally is that in the end, top performance requires both a match of technology and tools. Technology is going to come close to an inflection point because we are very close to the point in which it will be harder to scale down CMOS, and we will look at ways of enhancing CMOS and silicon, possibly with Schottky devices. We already have nanowires and nanosheets in existing products. So we are looking forward a change there, and we have to keep in mind the tools, the models that can be useful to attack these new circuits where you have new physical properties. I'd like to thank you for your attention, and of course I would like to thank my research group and my sponsors that are very important for achieving the result that I'm presenting to you. Thank you.
Thank you so much. This was great. Thank you so much. We appreciate it. And we have a proper certificate for you, something you will recognize. We visited this museum together once in 2002.
I'm really touched, yes. And I really like to visit it back with you.
We'll do that. We'll go again, but this is for you. I can translate it later. Thanks a lot.
Thank you,
Jim. These great plenaries will continue, of course. You will see more of them, but we also have our floor. The ITC exhibition floor has few hours left only. So we're closing about 1 o'clock, so make sure if you missed anything on the floor to be there. 1:30, I'm corrected by Ken. Thank you, Ken. So even more time, till 1:30, when we start the next plenary here by that time. Now, we also have on the floor the Global Test Forum. We also have the competition, the Air Force competition that I mentioned a little bit about earlier, the AFERX challenge. That challenge has been going on throughout these 3 days, and we have the chance to hear about the results. If Richard is here, can help in announcing. Richard, please come by. and this was a great novel thing that we added, and we'll get your feedback if you like it to see if we want to continue doing it again next year. So Richard will give us a quick briefing about it. Please.
Hi, everyone. So from the events this week, you might be aware that the Supply Chain Provenance Challenge has been going on. The concept is centered around being able to demonstrate the provenance of microelectronic components and assemblies in commercial off-the-shelf hardware. So I just want to start by thanking our commercial partners, Cisco and NVIDIA, for providing hardware and opening their doors to allow us to learn some about their practices and also provide data for comparison against the competitors' solutions. There were 3 teams that ended up here this week to compete. This all started at the beginning of the year. There was about 75 different solicitations that are proposals from the solicitation that was put out. There were 25 that were down selected in May at an event in Las Vegas. And out of that 25, there were 7 companies that formed the 3 teams. So over the last couple of days, we looked at the Cisco hardware on Tuesday, the NVIDIA hardware on Wednesday, and we assessed them based on the accuracy of their solution, the time that they were able to do it in, the total technical soundness, and then identifying any information that they would need to go in to better that solution. And so with that, I won't make anybody wait any longer. I know the teams have been a bit anxious, but if I could have a representative from the Brunel and Supply Dynamics team, please come up. The result was very close, and when I say very close, I mean within 1/10 of a point. So it forced us to take a very deep look at the score and make sure that we had what we thought we had. But I'm proud to announce that this team was the champion of the competition. So we have this plaque to recognize them. Thank you.
Here, you can hold that. There you go.
Excellent.
Thank you.
Congratulations. I just very good.
Picture 2.
Thank you. Please.
Thank you. Good morning. Sorry I'm late. I just came in from D.C. and downtown. The traffic was pretty bad this morning. I'm short on breath because I ran here to get here, but
Excellent timing.
I do want to congratulate these 2 teams, or this team and these 2 companies for all they've done. I watched the passion that went into this over the course of the last couple of days, and DefenseWorks is proud to support these folks, and we're going to give them $15,000 each as recipients for grant to further microelectronics supply chain. Sorry about that.
That's okay, man.
Thank you.
Thank you.
Thank you. Appreciate it.
Thanks a lot. Appreciate it. Congratulations.
Thank you, sir.
Congratulations.
Thank you.
All the best.
Thank you.
Thanks a lot for bringing this big competition here at ITC by Air Force and company. Also, thanks for the generous gifts that we just saw. Continuing on, also on the floor, besides the competition that we saw, we also have the Global Test Forum. The Global Test Forum also will be there again for the last window of time. We announced 3 windows of time. The last will be from 11:30 to 1 today. If you haven't been there yet, or if you need to visit the new elements there, you can do that. Yesterday, the Global Test Forum was quite busy. The different conferences, you see here examples of what we have: ETS, CTC, the Chinese Test Conference, that is, Northeast, as well as others. So please do visit the floor and bring in your information there. The awards. As you remember, we're announcing different achievements through TTC here, and I have 2 more questions for you for now. I'll give the answers after the visionary talk. The first one is for weighted author publications. This is which authors have highest weighted publication score after discounting based on the number of authors. Okay, so based on discounting the number of authors, who has the highest. Also another one would be which authors have the highest weighted publication score after discounting based on number of authors and account for the number of citations, so that's factored in as well. Again, a reminder that this is not based on Google Scholar, but it's based on, which was hard to find the information in an automated way. As Jay explained it yesterday, this is based on IEEE Explore, and these are the ITC papers, okay? Your mobile app, please do keep uploading the information, your communication, as well as the photos. We'd like to see more of your photos uploaded there. We do have the competition on the best photo to come, again, uploaded in the app. Don't forget to also provide your input, your evaluations on the yellow cards. Yellow cards are more practical, we heard. A few years ago, we did an electronic way through the app, but some of us did not like it, apparently. If it's on paper, we do it more systematically. We're used to these yellow cards for 50 years, I guess, and for now, we're continuing with it. Our visionary talk. This morning, our visionary talk is coming from Teradyne. Teledyne, as you know, is one of the giants in the ATE domain for a very, very long time in the history. They are part of our exhibition, have been for a long time. Now, the person who will present on behalf of Teledyne today is the president of Semiconductor Test Division of Teledyne. Greg Smith has joined Teledyne in 2006 as a semiconductor test product manager initially. He has served in a variety of roles at Teradyne, including manager of the complex SoC business unit, and then as vice president of SoC marketing in the Semiconductor Test Division, and currently he is the president of that division. He has over 30 years of engineering, management, and marketing experience in the semiconductor test domain. Mr. Smith earned his bachelor degree in electrical engineering from the University of Pennsylvania. Greg?
Wow, Coldplay. I feel like I'm far too pragmatic to be a visionary. And perhaps this talk is more how vision turns into reality than vision out into the future. Because back in 2013, we had just brought the 3rd generation of instrumentation to market in our UltraFlex tester. And we needed to step back and reflect where we were going to go and where we were going to take the tester. And part of that was doing a lot of work with our customers to try and get their feedback about where they thought that our architecture needed to go, where they thought our tester needed to go. And we discovered something interesting. In the past, when we were doing this, we were hearing people say things like, we need denser instruments, we need more megahertz, we need easier to use software. Now, all of a sudden, all of those messages were changing. We were getting far different information from our customers, and we were seeing different trends in the market that had nothing really to do with the things that we were traditionally hearing. And so, based on that, we placed a $500 million bet on re-architecting the UltraFlex on the inside to try and meet where we thought the market was going. And so what I'm going to be talking about today is where those trends, what we saw in those trends, how we derived requirements for the tester from those trends, and some of the elements of the architecture that we implemented. So what do we see right now? Back in around 2010, we were pretty paranoid. We had seen we were in this period of time where every human being on Earth was buying their first smartphone. The electronics industry was going crazy, and at the same time, the ATE industry was shrinking. And we were petrified of what was going to happen when the last human being on Earth bought their phone. We didn't know whether the market was going to go away. We didn't know what was going to happen, but it turns out that that was actually a positive inflection point. That once all those billions of people had phones and were connected, new applications for that connectivity started emerging all the time. And those applications drove a tremendous demand for more power, more data, more memory. And that actually has driven the ATE industry harder than the period of time where people were all starting to get that capability in their hands. A big characteristic of this change is that the market is being very strongly driven now by delivering processing power, by delivering connectivity, RF connectivity, huge mobile network capacity, and gigantic storage, both mobile storage and also in the cloud. So those common requirements are driving trends in the individual device segments. In processors, the key trends are moving to process technologies as fast as they become available, becoming process drivers. We're seeing the adoption of novel architectures to solve computational challenges that von Neumann architectures are not well suited for. And we're also seeing accelerating quality standards in all segments of the market, automotive, consumer, and in infrastructure. In the mobile network, one of the reasons that Teradyne has had a very good year this year is because of the build-out of 5G infrastructure. The 5G infrastructure is building out very, very rapidly, and the build-out of the millimeter wave infrastructure is happening far faster than anyone was predicting. That the desire to try and deliver huge amounts of bandwidth, especially to huge groups of people, say in an arena, is driving the adoption of millimeter wave. That huge torrent of data coming through mobile is also driving huge demand in terms of backhaul. And then in the memory market, flash is just continuing to grow. The desire for people to be able to carry every photo that they've ever taken in their entire lives on their phone, their ability to carry their entire media library with them at all times, that's driving flash to ever higher densities. DRAM, dealing with 8K screens on a mobile device, is driving bandwidth on DRAM to extreme levels and driving rapid adoption of new generations of LPDDR. And to our surprise and delight, hard disk drives are still a thing with cloud storage. And now the big thing in the hard disk drive market for us is that there's no such thing as cold data storage. That for backups and for older data, it's no longer being put on tape. It's being put on gigantic disk drives that are being used for storage, and that's helping to drive the whole hard disk drive industry. So this is, if we're at an ITC and we're talking about chips, then there has to be at least one slide with Moore's law on it. So maybe that's a different law, like a meta-level law about the test conference. So here's mine. The key thing is that I've been in semiconductor test for 25 years, and people have been saying that Moore's law is run out for the entire time. And this is a very recent set of data sourced from Wikipedia against 3 of the leading manufacturers of application processors. So in the period from 2013 out to 2019, the trend is actually running ahead of what's typically considered to be Moore's law rates. So this is being driven entirely by a battle for dominance in the mobile space by Huawei and Samsung and Apple and Xiaomi and Vivo, all trying to become dominant in that space to gain share by adding features and adding capabilities. So they're racing to try and get as much technology into the phone at the best power that they possibly can. So what's the impact of trying to drive this kind of complexity? That means that these companies are traversing process nodes every year to every 2 years. So it's a rare thing that they will actually put 2 generations apart on the same process. What's the impact of that? Every process has a natural yield learning curve where you start at relatively high yield losses, and then over time you're able to refine your rules, refine your tests, and get to higher yield. These customers are always living, These customers are always living on the steepest part of that yield learning curve. So how does that impact ATE architecture? The key impact to ATE architecture is that one of the most important requirements for ATE right now is actually ATE as an engineering tool. How can ATE enhance the ability to traverse that yield learning curve as quickly and efficiently as possible? We have customers that are spending dozens of testers, 24 hours a day, 7 days a week, gathering terabytes of data to try to get as much yield learning done as quickly as possible, and that ends up having a much larger economic impact than the ultimate cost of test of the device. So it's reversed the whole thing, where in prior generations of ATE, we were thinking first about production test cost, and as an afterthought, we would be like, oh yeah, I guess we should integrate with those vendors to help with the data analysis as an afterthought. What we have found now is, for this generation of tester, we had to put the efficiency of the tool as an engineering tool to be one of the most important requirements that we served. The other impact of serving this market is the relentless, the unrelenting day when Christmas and Lunar New Year happen. No matter what happens in your engineering project, those dates stay the same. And so the product launch dates stay the same. The only difference is that every year it gets harder to get the part done. The part gets bigger, so going from 14 nanometers to 7 nanometers more than doubles the amount of engineering effort required to bring that part to market. And the programs to test those, there's only 3 buttons. You'd think I could learn to push the right one. Those programs are getting bigger. So the amount of scan test time is increasing proportional to the amount of transistors in the device. And as I said, this is gathered from our own internal data over time across multiple customers, that we've seen a significant increase in the quality requirements for our customers to try and get to where they need to go. So you have these 2 factors, more transistors to test, higher test quality, that are both driving larger, more complex test programs. Again, this is putting an emphasis on the tester as an engineering tool as much as it is a production test tool. Because now you need to be able to get these 500 staff years in a year done. Since you don't have any flexibility on the total duration and the amount of work is increasing, the end result is that test development teams get bigger. And as test development teams get bigger, the optimization of the development environment for large development teams is critically important. And I'll talk a little bit about what that means in terms of the software architecture when we get a little bit further here. So interface complexity. I don't know how many of you spend a lot of time in a production environment, but this is what a probe card, the probe card without the needles, looks like these days. And there are 2 parts of it. There's a base board, and then there's a multi-layer organic interposer that goes on top of it. The probe card, the PCB, is down here. It's about 1 centimeter thick, 60 layers of PCB there. There's about 6,000 to 8,000 components between the PCB and the MLO. And here's a zoom in. This is the finest that an iPhone can do. A zoom in of the bypass capacitor arrays that are on the MLO. So, there's probably 100 in the size of a penny. In order for us to achieve the kind of yield and quality for our interface products going to the field, we've actually had to resort to developing advanced vision processing jobs to be able to do the inspection. So you can see in the background, see the picture on the screen of the computer in the background? That's taking pictures of that probe card and processing them against visual limits to make sure that all the components are present and all of the tolerances are met. So if you want a visual explanation of why parallel test trends have flattened out, this is it. In order to achieve useful yields and reliable production operation, we're already essentially at the very edge of what's possible in PCB technology and manufacturing technology. So if you look at this over a broader period of time, there are a couple of constants that have been going on in the market. The first constant is that our end market, the IC market, has been growing about 9% per year. And it wiggles around, but there's no discernible trend to it speeding up or slowing down. The other thing that's a constant is that devices are always getting more complex. Every year, every new process, devices are getting more complex. But over the period of time from 2000 out to about 2013, we are in a period of rapid innovation. And the rapid innovation was in two main places. The first was in DFT. This was the era where scan compression was making fantastic progress, and built-in self-test was making fantastic progress. And the net result of all of that was that even though transistor counts were going up geometrically, external test times were actually quite stable. Then you layer on top of that, it was also a period of rapid innovation from an ATE perspective, where Teradyne and Advantest were cranking out new generations of instrumentation on about an every 3-year basis that was doubling the density and enabling a doubling of the tested site count. So when you put those two things together, you can have a market growing at 9%, you can have rapidly increasing device complexity, and a tester market that's actually shrinking. So what changed? The big things that have changed are that device complexity is, if anything, accelerating, as we're seeing in terms of running ahead of Moore's Law, and all of the tricks that we've played to try to counter that device complexity at this point have run out. So there's still incremental improvements that are being made in DFT efficiency, but they're not keeping up with the device complexity. And because of interface complexity, we can still develop testers that have more dense instrumentation, but we're bottlenecked at the interface to the device. So as we're architecting a next generation tester, we needed to look at these two bottlenecks, and the tester as an engineering tool, dealing with the data, and then the bottleneck going to the device. So if you look at the wonderful predictions, I don't even know why we look at predictions because they're never right, but the predictions are that these trends are going to continue, and the amount of money that's being spent now is going to be increasing over the next 4 or 5 years against both testers and these interfaces. And when we look at this, we see that there is an unmet need. Essentially, there are customers that are going to want to fight against this curve, and they're going to look to people to create innovations to try to help control the costs of what they're doing. We want to make sure that we're the people that are delivering those innovations versus somebody who's going to come eat our lunch. So that's one of the things that's driving us to try and get towards an architecture that allows us to bend these curves. So here's some of the requirements that we came up with for this kind of a tester. So of course you have to be able to test the part. That's bottom line. You always have to be able to test the part. Key requirement is to attack customer time to market. Parts are more complex, they're harder to do. How do you make sure that people are able to manage large test development teams and climb the yield curve as quickly as possible? And then finally, how do we attack cost? And our fundamental belief inside of Teradyne is that the best way to reduce cost is to test parts faster. That if you can test more parts or test parts faster, you end up with better cost of test. And then we are expecting that over time there are going to be new DFT innovations that are coming along. One of the most exciting ones that I'm sure other people have been talking about at great length at this conference is serial scan, which is something that could definitely have a curve-breaking effect and something that we want to make sure that our architecture is capable of accepting. And then the other thing that we recognized is there's a law of diminishing returns. As parts become more complex and the total fault universe becomes larger, that it may make sense to limit coverage at earlier test stages and allow those faults to be found later through system-level test. And this is kind of, it's like heresy to be saying it, that it bred into us as young test engineers was this law of tens, that it costs you 10 times as much to find a fault each step down the line from wafer sort to final test to product test to in the field. But when it costs you twice as much to get another 9 on your coverage at wafer sort, then perhaps it's better to let those leak through into system level test, because the numbers of throwing away those devices in packages is actually far more cost effective. So we're like, okay, system level test, probably a thing, something we want to be able to do too. So how do we provide a highly productive development environment? Over and over, and this is the least visionary thing you're going to hear in any of the visionary talks, is what our customers tell us they want from a development environment is a development environment that's stable, that it doesn't crash, that it works all the time. And so we paid a lot of attention to not trying to inject too much change into this, especially in the user environment, and to focus on robustness. That we keep a consistent use model over time, and that we make it extensible through semi-custom tools. These devices are so complex and the teams are so big that there are often parts of test development teams that are just tool makers for the rest of the team. We need to make sure that our environment is appropriate to interface to that. And more than ever, we have to tightly integrate with our EDA partners. And I think of this as moving ATE EDA integration from PowerPoint into the tester. So this is an important change that we have to be ready for. At this point, most of our customers have been building these parts for a long time, for a decade or longer. And they are able to do these annual schedules because they are leveraging IP that they have confidence in. Same thing is true for test. We want our customers to be able to leverage all of the test IP that they've developed as they go into next generation testers. So that was an important requirement that we were paying attention to. And in order to support large teams, we need to be able to do true modular test program design. Next requirement, what can we do to simplify the device interface? How do we make it easier to connect to more complex parts? How do we break some of the bottlenecks that keep people from being able to get to higher site counts? And then attacking cost, making the tester faster. How do we minimize data log overhead? That's both for production and also to make the tester a better engineering tool. And how do we minimize the overhead associated with parallel test? And then recognize that our customers are probably going to want to complement what they do on ATE with system level. Take a big step back from the podium. Recognize that they're going to want to complement what they do on ATE with system level test, and how can we enable that process as seamlessly as possible. So the first thing we did in looking at this tester was we decided that we need an architecture that looked a lot more like a router that tested parts than a tester that had a router. So inside of the architecture, we have a core 10 gigabit per second network. Each instrument has a high performance controller integrated into it, and the tester controller is essentially architected to just sequence through the test program, which is all down here in the instrumentation itself. We have an independent DSP compute farm that's all available, and the whole idea of this network is that the only time that happens in foreground is time that's actually being used to test the device. Whether you're testing 100 sites the same way or have to individualize by site, all of the overhead associated with managing that has to occur in the background so that the foreground is just device-limited test time. That's a key part of this architecture. The biggest impact of that is actually for the tester as an engineering tool. The UltraFlex has kind of industry-leading overhead when it comes to data logging. So if you're doing full data logging, the tester can data log 1.2 million fail bits in about a second. The next generation UltraFlex Plus, because of this architecture, is actually single-digit milliseconds. So essentially eliminating that entire overhead, and it can bring something like a 30% improvement to the efficiency of doing things like full wafer DV work. So practical impacts of that network. In terms of the interface, instead of designing the interface around the instruments, we designed the instruments around the interface that we wanted. So the interface that if you look at the existing architecture, it was designed around getting instruments in slots and then routing them to the device. And so what you end up with is routing. These are just power planes, but even the power planes are being contorted to try and get from where they're going to where they need to go. That ends up boosting the layer count because of the Manhattan problem, and it also ends up with that over time this has turned out to be too small of a form factor to handle all of the ancillary components that we need. The final problem that we have is as we're covering bigger devices, higher site counts, the planarity requirements for this interface become even more stringent. So the UltraFlex did pretty well with a 50 micron deflection with the worst case loading inside of the tester. So think about it this way, you put all of the instruments in one side of the test head, you pull down a probe card on it. This is measuring how much slant you have in the middle of the PCB. And across that little 2.5-inch square in the middle, we have about 50 microns of flatness. And so in the new architecture, we're like, okay, what's the right way to be able to design these devices? What we really need is to make sure that the instruments are evenly distributed across all of the devices that you're going to test so that you're able to route straight into where you're going. The next thing you need is it needs to be big. It needs to be gigantic. It needs to be the biggest practical panel size that PCB manufacturers can do because it's absolutely critical to give as much flat space on the back to allow people to put components without doing tricky stuff that makes things not production worthy. So what's the impact of the change, this architectural change in terms of just the way this is oriented? You get about 30% of the layers out of the board. So you go from 56 layers down to 44 layers. And because of the design of this, we can have completely asymmetrical instrument loading and maintain 5 micron planarity across the site. So this is the key thing, that we wanted to keep compatibility with the instrumentation and the software, but redevelop the tester around the parts of the architecture that we felt like were going to be stressed the most by the trends in the market. The last thing that we did was we made this architecture modular. And one of the things that enables us to do is to tightly integrate with EDA. Best example of this is scan over USB. We've worked with Synopsys in this case, where their entire tool stack for serial scan is running on our tester controller. It is running through a SerDes instrument that provides direct support for USB to the device, and then the device has Synopsys IP that takes the USB packets, fans it out to the scan chains, and collects the data back. So this has both a positive impact in terms of the number of pins needed for scan, and also allows for the external interface for scan to run at a faster rate, getting more, basically it gives you a much larger number of scan chains, so your scan chains can be that much shorter. So this has a very positive impact on cost of test and production test. So this is an exciting new thing that was enabled by this architecture. And then finally, recognizing that we're going to be in a world where it's not practical to get to defect-free levels coming from the wafer sort level, and we wanted to be able to get to those faults as cheaply as possible. And so that's essentially why Teradyne has gotten into the system-level test business. So finally, just to wrap this up, I feel like we're at the beginning of a new era, the era of complexity, where over the past, there was an era of functionality where people were building megahertz and picosecond testers. Then through the 2000s, where it was all about capital efficiency. Since around 2013, we've entered this new era of complexity where the tester has gone from just being a production tool to being an engineering tool. And the key things are really how quickly and efficiently you can deal with the data, how well you can interface to the device, and how well can you partner with other members of this ecosystem to try and deliver values to the customer. So with that, thank you very much.
Thank you. Thank you. Appreciate it. Excellent job. We're happy to offer you this nice plaque.
Awesome.
Thanks again.
What's it say?
It says 58 ITC.
Yep.
Offered to Gregory Smith by the chair, Irvan Surian, the United States, Washington, November 12 to 14.
Thank you so much. This is great. Thank you.
You're welcome. Thank you. Thanks a lot, Greg. Moving ahead, so I owe you answers for the questions that we asked first. Again, this study showed us that the weighted authors for publications, this is the highest weighted publication, discounting the number of authors, that is dividing by. We're getting two highest ranked authors in this case. Ken Parker is the first with 19.9 weighted score, and Chris Chakrabarty is the second with 18.3 score. So congratulations to both of them. And regarding the next question, which is, again, the weighted scores divided by number of authors and taking into account the number of citations as well, again, based on IEEE Explore. In this case, we get 5 authors with a range of scores, weighted scores, so the top 5 authors are here as well. Again, congratulations to all of them. Please don't forget to go to the exhibition floor. It's our last chance. Same thing with the global forum. And the 3 workshops are waiting for us at the end of the day. In between, we have one more plenary. We'll see you here at 1 p.m. Thank you.